You see that uh, the second part, major part of your course is about the oxidation and reduction reactions. During this part, we will be trying to know about various type of the oxidizing and reducing agents, the process in where these agents are involved, and then we will also be studying about the various type of the reactions involving the elimination of the hydrogen, cleavage of CC bond, and the reactions which involves the replacement of hydrogen by oxygens. And in addition to that, we will also be trying to study about those reactions where there is a direct addition of the oxygens, and some of the reactions where uh, the replacement of hydrogen is usually taken place by the oxygen, or the removal of the oxygens from the substrate during the reduction process. And also we will be studying about the cleavage through the reductions, that is reductive cleavage. So these are all the type of the reactions that we will be trying to know about. Meanwhile, I am sharing with you meanwhile I will also be sharing one of the other chapter number 17 there is another book you can that is by the Robert Neuman, chapter number 17, that also more or less discuss the same thing. That chapter from the Neuman book, Robert Neuman, you can take it as the for understanding. This Neuman book, Neuman chapter chapter number 17 from the Neuman book, you can take as an assisting tool to understand more about these things. So today we will be starting with the various type of the oxidizing agents. So the question is that what are the various type of the oxidizing agents that we usually dealing with in the organic chemistry. These are some of the organic some of the oxidizing agents. They are like the KMnO4, HNO3, H2O2, peroxides, similarly the periodinane. These are the kind of the oxidizing agents that we usually used in the organic chemistry. Now you need to know about the detailed mechanism and the reactions where these oxidizing agents have their role, and also you should know about that what should be the oxidation state after they are participating in the various type of the organic reactions. So these are the kind of the things that you should. So you can see that this is a list of the various type of the oxidizing agents that can be used for the oxidation process. For instance, oxygen can by itself can be used oxidizing agent. Similarly, ozone, hydrogen peroxide, fluorine, nitric acid. Similarly, nitrate compound, sulfuric acid, peroxysulfuric acid, peroxy monosulfuric acid, hypochlorite, chlorate, perchlorate. Similarly, the hexavalent chromium compounds such as the chromium, chromic and chromic acids or chromic trioxides, they can be used as the oxidizing agents. Similarly, the permanganate compounds such as the potassium permanganate can be used as the oxidizing agent. Similarly, the sodium perborate nitric oxides, nitrogen dioxide, nitrogen tetroxide, potassium nitrate, and the similarly the sodium bis mutate, and then the cerium, some of the cerium compound like the cerium ammonium nitrate and ceric sulfate. These are the kind of the common oxidizing agents that we usually dealing with during the organic reactions. These are some of the common reducing agents that usually we are using in the organic chemistry, like the lithium aluminum hydride. It is the most strong reducing agent. Similarly, the nascent, that is the atomic hydrogen. Similarly, hydrogen that is without or with a suitable catalyst, for example, Lindlar catalyst. You know about that. And sodium amalgam, that is sodium mercury, and then sodium lead alloy, zinc amalgam, diborane, sodium borohydride, compounds containing the iron such as the iron sulfate, and then compounds containing the tin ion such as the tin chloride, sulfur dioxide, dithionate, thiosulfate, iodide, hydrogen peroxide, hydrazine, and then dis-isobutyl ammonium hydride, Dibal. This is a special reducing agent that we usually used. I will tell you later on about the special application of this. And then similarly, the oxalic acid, formic acid, ascorbic acid, reducing sugars, phosphides, and then hypophosphites, and some of the that is the DTT, that is dithione, dithiothiotol, and then similarly the carbon monoxide, cyanide, carbon carbon black, and then similarly the trace 2 carbo ethyl phosphine hypochlorite. So these are the common reducing agents that we usually used. The oxidation process. Oxidation is actually the loss of electron or the addition of the oxygen to a reactant is called as the oxidation, or the loss of the hydrogen. This is also called the oxidation process. During the oxidation, what happens that one of the species which is being oxidized, at the same time simultaneously there is another species has to be there that is being reduced. So if there is a process of the oxidation, there should be a process of the reduction as well. Some of the thing that is being reduced, some of the other that should be oxidized. So they are the the interdependent process. If some of the substance has to be oxidized, the other has to be reduced. In the redox reactions, we usually see that there is a definite transfer of the electron, complete transfer of the electron from one species to the other. This happens normally during the inorganic reactions, but this is quite this is quite uncommon in the organic reactions, where we do not see quite the transfer of electron quite clearly. For instance, I can give you the example of the oxidation of secondary alcohol to the ketones, where you can't see that there is any transfer of electron occur, but you definitely see that there's a you see that the oxygen, the oxidation state. So this is a very less common, the transfer of electron in the case of the organic reactions. So whatever the criteria that is fulfilling by a reaction, we say that the oxidation has occurred. Whether there is a loss of the there is a loss of hydrogen, addition of oxygen or the transfer of electron from a species. Whatever the out of these three processes has occurred, we say that the reaction, the species has been oxidized, and there needs to be a reactant that is responsible for this oxidations. We call that reactant as the oxidizing agent. So whatever the chemical species or the entity that is responsible for oxidizing another compound and reducing by itself, we call that as the oxidizing agents. And I have already named the various type of the common oxidizing agents that usually they are used in the organic reaction. Of oxidation, you will see in the organic reactions that they are very specific. Somewhere if we have more than for instance, if we have only one group that is required to be oxidized, it's very easy to try only a common oxidizing agent that will be able to oxidize that. But what about if we have more than one site for the oxidation and we specifically want to oxidize a particular part? Under that conditions, you will see that we need to use a specific oxidizing agents that is capable of oxidizing a particular part and without harming the other one. For instance, if you have a double bond and you also have the alcoholic group, so if you are required to oxidize the OH group to the ketone without harming the double bond, how to specifically bring about this reaction? Which of the oxidizing agent will be there which will be capable of specifically oxidizing that alcohol to the ketones or the aldehyde without harming the other part? So there definitely you need to have a specific oxidizing agent for that. During this course, during this chapter, we will be trying to specify and to describe the specific, the special characteristic of every oxidizing agent which differ that agent from the rest of the oxidizing agent. Every oxidizing agent has some special character that will differentiate that from the other. Some of the strong oxidizing agents are there which oxidize each and everything, just like the strong reducing agent. They do not differentiate between things, they indifferentiately reduce or oxidize everything. For instance, I can give you the example of lithium aluminum hydride. That is a strong reducing agent. Lithium aluminum hydride reduce each and everything mostly. Why? Because that is strong oxidizing agent. So that is not selective, right? That is not selective, because selective reducing agent is that one that selectively reduce only a part of the a particular functional group, but the inselective one reduce each and everything. So we usually avoid the lithium aluminum hydride being more reactive and inselective. But on the other side, you see that there are some other reducing agent which can only reduce a particular part, a particular functional group. So during this course, we will be trying to understand about the nature of each oxidizing and reducing agent. One basic thing that if you want to whether a particular species has been oxidized or reduced, is just look at the oxidation number. So if that is going towards positive, it means that there is a process of oxidation. If the oxidation number that is coming towards the negative, it means that there is a particular substance that has been. You can see here that on the left side, below 0, the oxidation number is going into negative, which means that these substances has been reduced. But on the other side, if you see on the right side of that 0, you see that the oxidations number, they are going in positive, and the more it becomes positive, then the number increasing in the positive order, you see that the more they are oxidizing. For instance, you see that for the RCOOH and then for the RCOOR, etc., etc., you see that the number of the oxidation number is increasing. It means that the oxidation level is. The question arises that what is the criteria for the oxidation? So you should look for these three steps, whether if they have occurred or not. If yes, if they are fulfilling this criteria, it means that oxidation has occurred. Number one, just look for the increase of the multiple bonds. For instance, going from the double bond towards triple bond, it means that this is oxidation, right? So increase in the multiple bond order of the carbon. Similarly, the bond order, if the bond order is increasing, it means that there is an oxidation. Second thing, you can understand whether the process oxidation has occurred or not. Just look at the addition of oxygen to a carbon. If there is an addition of oxygen, it means that there has been oxidation. Similarly, if there is a replacement or the removal of hydrogen or on a carbon, it means that or the replacement of any hydrogen with oxygen, you see that this is also oxidation. So whatever out of these three processes has occurred, we say that the species has been oxidized. For the redox reaction, that the gain in oxygen or the loss of hydrogen is oxidation. So thus, if we take the example of the alcohol, if we are oxidizing the primary alcohol, you see that will be changing into the aldehyde. If we are oxidizing the secondary alcohol, it will be oxidizing to ketones. Similarly, what about the tertiary alcohol? So tertiary alcohol is usually hard to oxidize. They will not be oxidized under the normal condition. What about the aldehyde? If aldehyde they are oxidized, you see that they will be changing into the carboxylic acid. So you can see here, this is the structure of the dichromate. You can put potassium on either side of this negative, because it will be all together. It's like K2Cr2O7, right? So if we remove the two potassium because they are ionic, so you can say that the rest of the thing that we are left with, they are the CrO7. I mean 2 CrO3, in between there is an oxygen, and we have two oxyanion. So you can put oxygen on either side. So it's a dichromate, right? Now this dichromate, we can also get this single chromate CrO3, where there will be a two doubly bonded oxygen. So you can say that this all can be used as the oxidizing agent depending upon the type of the reactions that you are dealing with. So you can also say that in the structure of the K2Cr2O7 is exactly the same as Na2Cr2O7, because sodium dichromate or potassium dichromate, only the metals has been changed. So both of these things have been used extensively as an oxidizing agent in the various reactions. It can bring about the oxidation of the primary or secondary alcohol into the respective ketones. Aldehydes are ketones. Similarly, you can also oxidize the aldehyde to the carboxylic acid. Somewhere the problem for you could be how to stop a particular reaction at a particular step, because if we go on to oxidize the alcohol, it may reach towards carboxylic acid, right? Because first suppose if we are talking about the primary alcohol, it will be changing into aldehydes. And if we are not stopping this reaction, it can go ahead towards the carboxylic acids. For instance, if we are required to stop the reaction at the aldehyde step, then what specific reagent, oxidizing agent we can try so that the reaction may not proceed towards the carboxylic acids. So that's the specific reaction where the cyclohexanone has been oxidized to and the cyclohexanone ring has been opened into the respective carboxylic acid. So it has been changed into the open chain dicarboxylic acid. You can try the mechanism of this reaction, how this could have happened. You can try on this mechanism. It's more or less the same. You can try on this and then come to me. Just propose the mechanism for the above reaction and then come to me. In fact, it is more like, but here the only difference is the manganese. So you can try on this chromium, because chromium, it's chromium CrO3. So just try on this reaction. And the oxidation of the cyclic ketone is difficult to bring about that with using the chromium 6 oxidation. I mean the reagent like the chromium oxide, CrO3, H2SO4 and water. That's why we use some extra amount of the acetone in addition to the chromium oxide, H2SO4 and water. So the mixture of these reagents collectively is called as the Jones reagent, and the type of the oxidation that it brings is called the Jones oxidation reaction. You can see that it can bring about the oxidation of the aldehydes to the respective carboxylic acid. Similarly, you can see that it can also produce chromium trioxide pyridine by abstracting a proton from the pyridine, and then two pyridine combines together and coming. So this CrO3 now is capable to attach with two pyridine. As with the start of the reaction, I have asked you a question that if we have the intention to stop the oxidation of alcohol at the aldehyde stage without taking that to the carboxylic acids, so what are the kind of the oxidizing agent available to us that can bring about that specific oxidation? I mean, if I'm starting with the primary alcohol, if this primary alcohol is subjected to the oxidation, it can go first to the aldehyde and then it can go towards the carboxylic acid. But if we have the intention to stop it at the aldehyde stage, then what are the kind of the reagent we have that can bring about the selective oxidation? So the answer for that is that you can try this complex oxidizing agent. And how to prepare that complex oxidizing agent? For that, you can react the chromium trioxide chloride with the pyridine, and then what would happen? It will replace the proton of the pyridine, and one of the pyridine with oxide with this chromium will attach with this chromium. And if we bring about the second, if we react another pyridine with this also, then we will be left with the complex where the two pyridine will be attached with chromium 3 oxide. So you can see that in this figure. So this is the complex where the chromium trioxide is being attached with 2 pyridine on either side. Now this is the kind of the reagent, oxidizing reagent that is capable of bringing about this selective oxidation. I mean, if we try it on the primary alcohol, it will only be stopped at the aldehydic stage. It will not take the reaction more towards the carboxylic acid. So this is called the selective oxidation. This is how you can make this reagent, that is by attacking the chromium oxide with the pyridinium salt, protonated pyridinium, where only the pyridine is then attached to the 2 oxides, and then making this complex and bringing about this complex formation on either side. If the chromium chloride, CrO3Cl, this is called chromium chloride, chromium oxide chloride, or chlorochromate. This is also called chlorochromate. If this chlorochromate is reacted with pyridinium salt, so this bring about the replacement of only one Cl group with the H, and then ultimately we get that PCC, that is called the pyridinium chlorochromate. But if the same reaction is repeated on the other side of the also, then we are getting the other also, that is called the pyridinium dichromate, that is called PDC. So this PCC and PDC, they are specific oxidizing reagent that usually we try in the organic chemistry to bring about the selective oxidation. You can see that the primary alcohol has been reacted with the oxidizing agent, that is the Jones reagent, and it has bring about the formation of the aldehyde in the first instance. In this way you can see that you can try many more reagent, that is primary alcohol, and then that will be bringing about the formation of the if you are trying the secondary alcohol, it will bring about the formation of ketones, and of course tertiary alcohol will be hard to. So you can see that during this reaction, the chromium is changing the oxidation state from the chromium somewhere from the chromium 6 to the chromium 4, and somewhere from the chromium plus 4 to the chromium plus 3. It means that the positive charge has been reduced on chromium after the reaction. So reduction in the positive charge means that chromium reagent by itself has been reduced, but it has allowed the oxidation of the other thing. That's why it's called the oxidizing agent, because every oxidizing agent by itself is getting reduced, but it brings about the oxidation of the every other thing. That's why they are called the oxidizing agent. Detailed mechanism for this reaction, that how this reaction taken place. You know that the OH of the primary alcohol, it usually react on the most positive electron deficient center, that is called the chromium. So after the attack, you can see that the oxonium ion has been resulted in the product, and then to get the stability, you can see that the oxyanion has taken the proton from the oxonium and gets stabilized by the way. And then what happens that the H of the attached to the OH, H of the OH group changes into the carbonyl group, and one of the OH is leaving as a leaving group. And then what happened, you see that there's a so the one of the oxygen has been lost, and then the next step is of course the proton of the alcohol, that is the attached to the carbon is being abstracted by the base and pushing the electron pairs towards the chromium and resulting into the formation of the ketone group. And in the last step you can see that the proton that is taken from the water by the oxyanion and resulting into a stable species that is called the H2CRO. So yesterday, for instance, if we have a site where the more than one sites are available, right, and we are intended to oxidize only one site, so how to bring about that? And for instance, if we have the allylic position, and if we want to bring something like the OH group or at the allylic position, so what are the available oxidizing reagent we have for that? The answer for this question is the manganese dioxide. You see that just see at the structure of the manganese dioxide and just think that what kind of you can see here that this reaction is again now a reduce selective reactions, because the reactant have more than one site for the attack, and ultimately you can see that only reaction occur at only one site. We have two type of the alcoholic function. One is the downward side at the downward side, and one is the upper on the upper side. The one at the upper side contains a double bond in conjugation, right? But there is no double bond at the below one. It means that the above one is the allylic alcohol, right? Now this allylic alcohol, you can say that this allylic alcohol, when you are treating it with the manganese dioxide, there is no effect you will be observing no effect on the below one, the one that is not allylic. But the allylic alcohol, you know, that will this manganese dioxide will bring about the selective oxidation of this allylic alcohol, and this will be changing into the aldehyde. So you can see that. Now why the other one is not? The second example, you can see that the aromatic ring is there. So you can see again the allylic alcohol. One is the allylic alcohol, benzylic alcohol, and the other is not the benzylic alcohol, right? So only the benzylic alcohol is being subjected to the oxidation, and ketone is resulting, but you can see that the other alcohol remains unaffected. Now this is the selective type of the oxidation, because the allylic or the benzylic alcohol, they are being oxidized, and the other type of the alcoholic group, they remains unaffected by using this selective oxidizing agent, so called the manganese dioxide. You can see here the mechanism of this reaction. This reaction proceeds through the free radical mechanism, because the manganese 4 MnO2 this generate the free radicals, and you can see that free radical, this bond between the this is the H bond that is homolytically cleavage heterolytically, and a free radical is now generating at the carbon. Now you can see that why this allylic why the allylic oxidation is stable compared to the other. That's why it is only the allylic position is being oxidized. The reason for this is that it resulting into the allylic radical, because allylic radical is more stable. By doing this, we can result into the allylic radical, and that is quite stable compared to the other one. That's why this allylic position is being oxidized using this manganese dioxide, the manganese 4 compound. You can see that the first step is that the alcohol, the OH group, the allylic OH, it attack on the manganese. You already know that this manganese is has the empty orbitals. It has the capability of accepting the lone pairs in it. So that's why the OH group attack on the manganese and the electrons are shifted. And then in the next step, what happens? The H attack on the homolytically attack on the oxygen. So H attack on the H radical attack on the oxygen, electrons are shifting into the manganese. And then what next? That it resulting into the allylic radical. This allylic radical, you can see that arrow. What this arrow indicate? This arrow indicate there is a coordinate covalent bond, where the lone pair of the electrons, they are from the oxygen towards the manganese. Once this bond is established, is formed, what happens next? The radical from the hydrogen, they are shifted towards the oxygen, and the bond between the oxygen and manganese is cleaved, and this whole pair is now shifting towards the manganese and resulting into the 2 OH group at the manganese, and it is attached with that O of the compound. And what next? In the next step, what happens? That the O and manganese bond is again cleaved, and one of the electron is coming towards the oxygen, where a double bond is regenerated, and this Mn leave with the H2 MnO2. So this is the final product. You can see that we can bring about the selective oxidation using the manganese at the KMnO4, that is the MnO4 that is resulting from the KMnO4. This MnO4 also oxidize the alcohol, but there is no condition for to be allylic or something. It can bring about the oxidation of any alcohol into the respective aldehydes and ketones. You can see that if we subject the primary alcohol to the towards oxidation through MnO4, the first step will be again the same. The OH group, the oxygen of the OH group will attack on the manganese. There will be a bond formation between the oxygen and the manganese, and then what next? There will be oxonium ion formation, and that proton can be abstracted by the oxyanion of the manganese, so thereby stabilizing this. And then what will be the next step? You can see here that in the next step you can see that the again you can see that the H now base abstract the proton from the carbon that is next to the oxygen, and then resulting into the and then that after the abstraction, that electron pair is moving towards the oxygen, and then the bond between the oxygen and manganese is shifted towards the manganese, and you can see there is the formation of the aldehyde. So if instead of the aldehyde if we have a secondary carbon attached to this oxygen, then that will be resulting into the oxidation through the sodium hypochlorite. using the sodium hypochlorite, the alcohol can be oxidized to the respective aldehydes or ketones. You can see that the mechanism for this reaction, the alcohol, you can in this mechanism you can replace sodium with H, right? This has the same mechanism, just replace the sodium with the now what could be the mechanism? Just alcohol attack on the Cl, and it abstracts the Cl group, and then what next? The sodium will be moving with the chloride, and then we will have this protonated OH group. In the very next step, what happens that the water or the alcohol we have in this case, that will be abstracting the H group, H hydrogen, and then the lone pair of this the bond pair of this hydrogen will be shifting towards oxygen, and there will be a double bond formation, and this Cl group will be leaving, that will be later on combined with the sodium to produce the sodium chloride. So this is the overall mechanism for the reactions when we are using the sodium hypochlorite. This is common for the oxidation of any of the alcohol, whether the now you have noticed one thing, that we are using this type of the oxidizing agent, whether we are oxidizing the, if we are oxidizing the primary alcohol, it is changing into the aldehydes, and if we are oxidizing the secondary alcohol, it is changing into the ketones. Now my question is there any possibility that we also oxidize the ketones? Because normally you see that the aldehyde can easily be converted to the carboxylic acid, right? But what about the oxidation of the ketones? Normally you wouldn't see the oxidation of the ketones, as they are more resilient, they are more resistive towards oxidation, the normal oxidizing agent. So we need something special to bring about the oxidation of the ketones. In order to bring about the oxidation of ketones, we need peroxy acid, peroxy acid, perbenzoic acid, or something like very strong oxidizing agent in the peroxy acid, also like the CF3COOH, trifluoroacetic acid. You can see that this trifluoroacetic acid contains a very high electron withdrawing group at one side. Now this is the kind of the reagent that can bring about the oxidation of the ketone as well into the respective esters. So ketones can be oxidized and can be changed into the respective esters using this trifluoroacetic acid. How this is possible? You can see this. Now the specific reaction for this is the Baeyer-Villiger oxidation. This Baeyer-Villiger oxidation, you can see that using this Baeyer-Villiger oxidation, you can bring about the oxidation of the ketone as well. There's an insertion of oxygen between the carbonyl carbon and the alkyl group. So you can understand this by seeing the mechanism of this reaction. How to synthesize the trifluoroPeracetic acid. The trifluoroPeracetic acid can be produced by treating the trifluoroacetic acid with the H2O2. If you are treating the trifluoroacetic acid with the H2O2, it will be resulting into the trifluoroperacetic acid. This peracetic acid is now capable of bringing the oxidation of the ketones into the respective mechanism. You can see that the first step is the protonation of the ketones, and once this ketone is protonated, the next step is the OH of the peroxyacetic acid attack on the carbon of the ketone and shifting that bond pair of between the carbon and oxygen towards the oxygen, subsiding that positive charge. And now we have in the third step, you can see there is a proton shift. In the proton shift process, you see that the we are getting this you can see there is a proton shift. Now in the next step, there is the migration of R group. And how this has happened, the oxygen, the lone pair of the oxygen is moving towards carbon, and when this lone pair of the OH is pushed towards carbon, the R1 group, this is shifted towards the oxygen. So now this is replacing the rest of the OCO-CF3 group, and this rearranged product is resulting. And after this rearranged product, we can see that there is a this proton is being abstracted by some by the share there by the base, and resulting into this stable neutral ester. Now this is, you can see that right from the beginning till the end, you can see that the ketone has been changed into the respective ester. Initially you can see that in the reactant, the RC double bond OR1, this was the reactant, but in the product you can see that this is RC double bond OR, right? So it means that during the course of this reaction, what has happened, the oxygen has been inserted between the carbonyl group and the R group, resulting into this ester, and now this is the stable product, Baeyer-Villiger product. So it means that using this peroxy acid or perbenzoic acid or peroxy acid, we are able to bring about the oxidation of the ketone as well. Normally you wouldn't see the ketones to be oxidized, but now using this peroxy acid or perbenzoic acid, they are quite capable of bringing about the oxidation of the ketone as well, the cyclic ketone as well, such as the cyclopentanone, cyclohexanone. If you are subjecting these ketones, the cyclic ketones, to the peroxy acid, you will be observing that the oxygen will be inserting between the carbonyl carbon and the alkyl carbon, and you will see that it will be changing into the respective ester. So this was something about the Baeyer-Villiger oxidation, that is the oxidation of the ketones or the cyclic ketones into the respective esters. So in today's lecture we have talked about the oxidation through the MnO2, that is the allylic and benzylic oxidation, and then we have also noticed and done the mechanism for the Baeyer-Villiger oxidation, that is the oxidation of the ketones. So we will be continuing this selective oxidations in the following lecture also. Bonds between the carbon and carbon. You know that whenever you have the double bond that are quite feasible site for the oxidation, if you have a double bond and if you have the nascent oxygen reagent reacting with that double bond, there's a possibility of the oxidation of this bond, changing this multiple or double bond into a single bond. This is the cleavage of the CC bond. And then sometimes this cleavage can be going further ahead, changing into the complete cleavage of the bond between the C and C. Sometimes it remains to the double bond. As you know about if you have a double bond, there's a first possibility is the formation of the epoxide ring, and then epoxide ring is opening, resulting into the diol. You know about various type of such reactions where there's a formation of the oxidizing ring, and then that ring is breaking down after the nucleophilic attack of the OH group or the water on the one of the side of the carbon, where there is an opening of the epoxide ring resulting into the diol. Remember that this type of the addition is the entire addition. We already know about this, where if the epoxide, the side where this epoxide has been formed, opposite to that side there's a coming nucleophile is coming as OH group, maybe in the form of water, and then there is a opening of the ring on the other side. So there will be an entire addition of that during this process and resulting into the diol. So entire diol is produced by this way. And then you know that can further go ahead, this oxidation process may continue and resulting into the respective aldehydes or ketones depending upon the conditions. If the other conditions they are feasible, then this oxidation process can go further ahead. For this purpose we use the peroxy acids like the perbenzoic acid or perchloroacetic acid. So various type of the metachloroperbenzoic acid. These are a number of the reagents that we can use for as the oxidizing agent for bringing the oxidation of the double bond. So today we will start with the oxidation of the multiple bonds between the carbon and carbon. You know that whenever you have the double bond that are quite feasible site for the oxidation. If you have a double bond and if you have the nascent oxygen reagent reacting with that double bond, there's a possibility of the oxidation of this bond, changing this multiple or double bond into a single bond. This is the cleavage of the CC bond. And then sometimes this cleavage can be going further ahead, changing into the complete cleavage of the bond between the C and C. Sometimes it remains to the double bond. As you know about if you have a double bond, there's a first possibility is the formation of the epoxide ring, and then epoxide ring is opening, resulting into the diol. You know about various type of such reactions where there's a formation of the oxidizing ring, and then that ring is breaking down after the nucleophilic attack of the OH group or the water on the one of the side of the carbon, where there is an opening of the epoxide ring resulting into the diol. Remember that this type of the addition is the entire addition. We already know about this, where if the epoxide, the side where this epoxide has been formed, opposite to that side there's a coming nucleophile is coming as OH group, maybe in the form of water, and then there is a opening of the ring on the other side. So there will be an entire addition of that during this process and resulting into the diol. So entire diol is produced by this way. And then you know that can further go ahead. This oxidation process may continue and resulting into the respective aldehydes or ketones depending upon the conditions. If there are the conditions that are feasible, then this oxidation process can go further ahead. For this purpose, we use the peroxy acids like the perbenzoic acid or perchloroacetic acid. So various type of the metachloroperbenzoic acid. These are a number of the reagents that we can use for as the oxidizing agent for bringing the oxidation of the double bond. So above you can see that on the rightmost side above, the structure of the metachloroperbenzoic acid. So basically it is oxygen rich species which need the oxygen. The in between oxygen which is attached to the OH group which is present in between the carbonyl carbon and the OH, that oxygen usually take part in the oxidation of the double bond. On the left side you can see that how it is attacking. First of all, what happens that the oxygen attack on one of the carbon. After the attack, this double bond is pushed towards the oxygen. So we see that once it is attacking on the oxygen, the bond between the oxygen is now shifting towards the carbon and oxygen. So there is the carbonyl bond formation towards the peroxy acid. You can see that the aryl group, and adjacent to the aryl group there is a formation of the carbonyl group, and then that oxygen is now attached to the double bond. So there is the formation of the epoxide. In the transition state you can see that we can draw the transition state for that as well. You can see that in the transition state there is the cleavage of the O bond, and there's the formation of the CO bond, another CO bond. So two of the CO bond they are formed, and the rest of the bond they are cleaved, and then at the end of the product you can see that the epoxide is resulting in this mechanism. If you further oxidize this can result into the diol just by attacking another nucleophilic attack of the water on this epoxide ring can result into the entire diol product. So this reaction is very common, and you are familiar reaction where the diol formation take place. Similarly, there is another reaction where there is a possibility of the diol. That is the oxidation of the double bond with the osmium tetroxide in presence of the sodium sulfide. So you can see here also that the osmium tetroxide, which is the oxidizing agent, can result into the diol formation. The same kind of the reaction can also be performed by the KMnO4 in presence of the base and water, also resulting into the diol. But this diol is a syn diol. In the epoxide we saw that is the entire diol, but this reaction result in the syn diol formation. So you can see the mechanism of the oxidation through the osmium tetroxide. You can see the structure of the osmium tetroxide showing the presence of the 8 bonds. I mean the 4 oxygens are attached through a double bond. Each of the oxygen is attached to the double bond. So there are 8 bonds altogether. You can see that now the double bond of the alkene attack on the oxygen, pushing the electron pairs toward the osmium, and then the other electron pair from the oxygen attack on the other carbon. So there is a cyclic intermediate formation where the two oxygen, they are attached to the two carbon. Now this product, after the workup, they are, after the cleavage, they are resulting into the, after the acid workup, they are changing into the diol, into the syn diol. Syn diol is the product that is resulting after the oxidation through this osmium tetroxide. Syn means that two of the OH group, they are present on the same side. So if they are present on the opposite side, just as in case of the epoxide opening, that will be the entire. But here in this case, it is the syn addition, that is the two OH group will be added on the same side. The same sort of the mechanism is also with the, when we are using the manganate, MnO4. So but the only difference is that osmium tetroxide has the 8 bonds, but the manganese, central manganese in the manganate, you can see that it has 7 bonds altogether, and one of the oxygen is bearing the negative charge. So you can see that the same sort of the mechanism is also there for the when we are using the manganese, the double bond attack on the oxygen of the manganate MnO4, and then pushing the electron pairs toward manganese, and the other electron pairs that is coming to the towards the other carbon, resulting in the cyclic intermediate. You can see that in this cyclic intermediate, then after the workup with the acid, resulting into the diol, syn diol again. So both of these reagent, that is whether osmium tetroxide or the potassium permanganate, they have the same mechanism and same result, because both result into the syn diol. Osmium tetroxide gives a very good yield of the 1,2-diol. This is also called 1,2-diol. But the only one thing is that it is toxic. Usually it needs proper handling, because it causes blindness, right? And most importantly, they are also expensive, so highly expensive. On the other side, the potassium permanganate is inexpensive and safer as well. So if we are left with the choice that whether we should use the osmium tetroxide or the potassium permanganate, the preferable choice would be the inexpensive and the safer potassium permanganate. Though it's gave a very low yield of the diol. So both of these have some advantages and some disadvantages. If we compare the osmium, the oxidation through the osmium tetroxide gives very good yield, but the problem is it's toxic and it's caused blindness, needs proper handling. On the other side, if we are using the potassium permanganate, that is inexpensive, that is safer, there is no toxicity associated with that, but the disadvantages of the potassium permanganate is that it gives a very low yield. So you have to compromise with one thing, whether if you have the proper handling, and if you can afford, then you can have a very good quantity of the diol using the osmium tetroxide. But if you are don't have the proper investment, and then the preferable choice would be potassium permanganate, but the overall yield would be using less. The H2O2 has the same kind of result as you obtained while using the perbenzoic acid, metachloroperbenzoic acid, or peroxy acid. This H2O2, that is the that has also the same sort of the result, resulting into the epoxide ring, and then after the acid workup you will get the 1,2-diol that will be entire to each other. The 2-diol will be at antipositions to each other, so that will be the entire addition, because the coming nucleophile, that is the OH group, water, that will be attacking on the opposite side where this epoxide is present, and resulting into the entire 1,2-diol product. This is exactly the same as you saw in case of the perbenzoic acid. So question is that what are the conditions where we have a complete cleavage of the double bond? I mean the type of the oxidation reaction where there's a complete cleavage of the CC double bond. The type of the oxidizing agents such as the ozone or the chromium trioxide and the KMnO4. We have already discussed KMnO4 previously, just a while ago, but in that case we didn't do the acid workup. I mean we didn't proceed that, but if you proceed that KMnO4 with the acid, you will see that there will be, instead of the diol, it will ended up with the complete cleavage of the CC bond, resulting into the ketone or the aldehyde. I already told you before. But here you can also get the results of the cleavage of the CC bond using the ozone and the chromium trioxide as well. Suppose you have a compound, a double bond, and across the double bond there are substituent, that is at one side there is substituent R1, and on the same side there is R2. On the other side of the double bond there is R3, and on the same side there is R4. So you will see that after reacting it with the ozone or with the chromium trioxide or the KMnO4 with acid workup, you will see that this bond will be cleaved, resulting into the two ketones. One of the ketone will be R1, R2 oxygen, I mean ketone. On the other side, the ketone resulting would be R3, R4, and the carbonyl carbon, that is the ketone. So you can, the very simple way to understand this is just cleave the double bond in between, so some of the substituent, and put the oxygen on either side of this double bond. So you will get two type of the ketones. But if the substituent on either side, they are, some of the substituent they are hydrogen, you will get the aldehyde as well, right? It depends the kind of the substituent on either side of the double bond, because this is a complete cleavage of the double bond. The mechanism of this reaction can be understood by the way you already know about the ozone, but I will show you that how it proceeds. So in this mechanism, you can see that the ozone structure consists of three oxygen, where the terminal oxygen bearing a negative charge and the central bearing a positive charge. And then with the start of the mechanism, you can see that the terminal O negative oxygen attack on the one of the carbon of the double bond and of alkene, and then what happens, the pi electron of alkene is pushed towards the other oxygen, doubly bonded oxygen, and that doubly bonded oxygen push the electron towards the central one, and resulting into the cyclic structure that is called the molozonite. So this molozonide is the first cyclic structure that is resulted after the attack of this ozone on the alkene. What happens next, that you can see that all the three oxygen, they are in one row. So this structure is highly unstable. This is the intermediate, in fact. So this intermediate now moving on towards a very stable structure. First of all, it is cleaved. It cleaves at the where the lone pair of the oxygen is pushed towards the carbon, and then the carbon-carbon bond of the alkene that is cleaved and that is pushed towards the other oxygen, resulting into the carbonyl carbon, right? So alkene is changing into the carbonyl carbon, and that oxygen, the bond between the oxygen and oxygen is pushed towards the oxygen as a negative charge. So during this process, you can see that the ultimate result is the formation of the two fragments. One of the fragment is the one where the consisting of the O negative oxygen, central oxygen with positive charge, and doubly bonded carbon. So this is what we get, and the other product is the stable one, that is the aldehyde, right? Now what happens, this two intermediate rearrange in such a way that the O negative part of that is towards the carbonyl carbon, and now it attack on the carbonyl carbon. On the carbonyl carbon, it is a nucleophilic attack on the carbonyl carbon. After this attack, what happens, the oxygen lone pair of the carbonyl carbon attack on the double bond, and the double bond pi electron is pushed towards the oxygen. So there is a formation of another cyclic structure which is even more stable than the initial cyclic structure, that is the molozonide. This structure is called the ozonide, right? So this ozonide is comparatively more stable than the molozonide, and this structure still have some instability, and the PPH3 triphenylphosphine is now there. This is the oxygen absorbing species, which resulting into the this is electron deficient center, and then what it does, it abstract the oxygen, nascent oxygen. How? Just by attacking of the oxygen. In fact, the after the attack, you can see that there is a formation of the carbonyl group again. Along with this, in fact, two of the carbonyl groups, two of the carbonyl compounds are resulting. One is the formaldehyde, and the other is the simple other aldehyde. Along with the PPH3, PPH3 along with double bond. So you can see that the stable triphenylphosphine oxide, this is a stable species that is resulting, and the ultimate product of this ozonolysis is the formation of the two carbonyl compounds, the formaldehyde and the other aldehyde, along with this triphenylphosphine oxide. So you can see there is a cleavage of the double bond that has taken place during this entire reactions. If I just want to simply understand without the mechanism, I just want to look at the reactant, and then I want to predict the product. So how can I do that? Just look at the reactant, that is the alkene. What did you see from there? You can see that the structure of alkene is as such, where there are two hydrogen at one terminal site, right? I mean CH2 double bond, and then H and R. This is the structure of alkene. So if I cleave this alkene at the central point, what are the products that I can see? Of course, there are One will be the formaldehyde and the other will be the simple aldehyde. So this is what I got in the product also. So this can be predicted before even doing this mechanism, that what should be our product, just by cleaving the central double bond, and then on either side whatever the substituents are there, they will be resulting. So this is a complete cleavage of the double bond. One thing is important, instead of PPH3 you can also use the zinc as the oxygen absorbing species, because you need something that can abstract the oxygen. Zinc has also the capability to take that nascent oxygen to resulting into the zinc oxide. So we can replace this PPH3 with the zinc using the chromium trioxide. Also cleave the CC bond resulting into the respective ketones. First of all diol and then ketones. Similarly you also saw the osmium tetroxide, which we have initially discussed, that particular compound result into the diol, syndiol, like the KMNO4 or the osmium tetroxide. They result into the diol. But if we treat after the acid workup, that can be cleaved into a complete, similarly using the HiO4 and the lead tetraacetate, though. So the main mechanism for the HiO4 and the lead tetraacetate is exactly like the KMNO4. The only difference is that instead of the MnO4 or the osmium tetroxide, you can put that iodate like the IO4. So there will be 4 oxygen around the iodine, and rest of the mechanism is exactly the same as that of the osmium tetroxide. Similarly, tetraethyl acetate has the same mechanism. The only difference will be the tetraethyl acetate, that will be the lead will be the central metal, and around that there will be 4 acetate. So you can proceed that with the same mechanism, and the ultimate result will be the formation of diol initially, and then after the acid workup there will be a cleavage and resulting into the 2 ketones. So you can also see this oxidation using the tetraethyl lead. The mechanism, you can see that initially there's also possibility that you can also proceed with both of the base, starting with the lead tetraethyl acetate, or initially you ionize that into one OEC will be leaving, and then what happened, this Pb positive, now this is being attacked by one of the OH group, and it is attached to one of the OH group, for resulting into the oxonium formation, and then leaving the H, subsiding the positive charge. And then what happened next is that OEC is leaving another OEC, and then still getting another positive charge on the Pb, or the double bond you can make. So by that way what happens, that the another OH attack at the Pb center, resulting into the cyclic structure. And then what happens, the leaving OEC can abstract the proton of the oxonium, subsiding the positive charge. And then finally the final step is the cleavage step, where there is the formation of the 2 ketones. So you can also follow this mechanism, whether you are dealing with the HiO4 or you are using the lead tetraethyl acetate. lead tetraacetate. In both of these, you can see that they are responsible for the cleavage of the diol. So there is an initial diol, and then diol is then cleaved by the HiO4 and the KMnO4. HiO4 tetra lead tetraacetate and the HiO4, that is periodic acid. So you can see that the KMnO4 and the osmium tetroxide were the ones where they produce the diol, and then finally this periodic acid HiO4 and then lead tetraethyl acetate are the ones that can cleave that diol that has been resulted by the osmium tetroxide and the KMnO4. So those diols which are resulting by the oxidation of the KMnO4 and osmium tetroxide, they are cleaved completely, resulting into the respective ketones or aldehydes by the reaction with the periodic acid and the as well as the lead tetraacetate. So this was the oxidation, and this was the various type of the methods that today we have discussed. Oxidation exists in the two electronic form, singlet. In the oxygen exists in the singlet oxidation state, and in the triplet oxygen that is present in the air, in the atmosphere, also carried out the auto-oxidation because it occurs in the two electronic state, that as I told you, it can by itself act as the oxidizing agent. It is present in two electronic form, the triplet form and the singlet form. Today we will see some of the reactions where the oxygen is participating, is playing a role of the singlet oxygen. We will see some of the reactions where the oxygen play a key role as a singlet oxygen. We will talk about the triplet oxygen reactions later on. Today we will see that what are the various reactions where the molecular oxygen act as the singlet oxygen form. We can see that there is a single electron on each oxygen, right? Each oxygen bearing a single unpaired electron. We call that as a triplet oxygen. But in the molecular oxygen, where we have the O double bond with O, we see that the unshared pair electron, there is a lone pair of electron is present on each oxygen. We call that as a singlet oxygen. So you can see that in the first example, the first reaction, you see that we have this double bond attached with the single bond. So single and double bond, they are alternatively attached with each other. On the double bond, you can see that there is one hydrogen, right? Two hydrogen, in fact, on the terminal double bond. So there is an insertion of oxygen occur between the C and H, resulting into the you can see that it results into the hydroperoxide. This is the first example. You can see that the oxygen is inserted in between the carbon and the hydrogen, and resulting into this product number 1. In the first reaction, you saw that the oxygen inserted between carbon and hydrogen resulted into the hydroperoxide. What about the second diene? When the oxygen reacts with the diene, you see that it results into the when the singlet reaction react with the diene, conjugated diene, it gives a cyclic peroxide. This is the second product. This singlet oxygen reacting with the diene, resulting into the cyclic peroxide. This is the second product. In the third product, you see that sometimes it's possible that it react end to end and resulted into the four-membered dioxetane ring. This four-membered ring we have studied in the last semester that this four-membered ring is highly unstable. Why? Because cyclobutane has the torsional and the angle strain by itself, but if some heteroatom is coming into it, that will make the system even more destabilized, and ultimately it has to break down into some stable product, that is the ketones. So this is the third type of the reaction that are usually observed when dealing with the singlet oxygen. So you come to know that singlet oxygen has three types of the reactions, whether either it will be inserting between at the terminal bond between the carbon and hydrogen, resulting into the hydroperoxide, or it will be inserting into the diene, resulting into the cyclic peroxide, or it can sometimes produce the four-membered ring by reacting with the double bond, that is the highly unstable ring, and that is the oxetane ring, and which finally break down into the carbonyl ring. So usually we see such kind of the reactions in the benzene, in the oxygen. Now the next section is that what are the what will be the result if we are introducing certain compounds having the alkyl chain. What will happen if they are subjecting to the oxidation? So we see that certain reactions where we have some side chain that are feasible for the oxidation, they will undergo the oxidation process and will be resulting into some oxidation. In this reaction, you can see that if we have the alkyl group attached to the double bond, there are two possibilities. Either this will be partially oxidized or it will be completely oxidized. In the partial oxidation, you can see that the side chain has been changed into the alcohol. Initially there was an alkyl group, but the partial oxidation has taken it to the alcohol. But the complete oxidation has taken into the carboxylic acid, right? Similarly, there is also a possibility that the central carbon result is oxidized and resulting into the ketones. So there is only one reactant and we have three kind of the products. So three possibility for this reactions when it is subjected to the oxidation. Either it will be changing into alcohol, or it can be changing into carboxylic acid, or it can even change into ketones. So it means that three distinct oxidizing agents will be involved in this reaction that can change this reactant to. Now the question arises that what are the reactions that can take it to the carboxylic acids? We have seen a number of such reactions and we have studied it in the last lecture and the previous few lectures, that when the alkyl side chain is subjected to the metal oxidations like the KMnO4 or the other metals or the chromium oxide, we saw that it is changing into directly into the carboxylic acid, that is there is a complete oxidation of this, and alkyl chain. But on the other side, you will see that the chromyl chloride, that is the Cl2CrO2, if the same reactant is subjected to the chromyl chloride, instead it take it to the carboxylic, it will only be oxidized till the aldehydic stage. It oxidizes the side chain only to the aldehyde, but if we subject it to the KMnO4, it will take it directly to the carboxylic acid. What about the selenium oxidation? Selenium oxide, SeO2, if we subject the double bond alkane, we will see that the allylic position will only be oxidized. It will be oxidized to the alcohol. Similarly, if we react the benzylic group, it can also be taken into the carboxylic stage. So this is called the selective oxidation of the selenium oxide. You can see that if such kind of the ketones they are introduced to the oxidation with the selenium oxide, you can see that they are changing into the carbonyl group. Similarly, if the alkanes are introduced in presence of the light, there will be free radical type of the reactions where there will be an insertion of the oxygen between the R and H group, resulting into the hydroperoxide. Auto oxidation is sometimes could be an unwanted reaction. For instance, let's suppose we are conducting a free radical reactions between two alkyl groups. We are using the light as a source for the free radical reaction, and we are generating the one alkyl group and the other alkyl group as R radical and R radical, and the intention is to combine these two, resulting into a different alkane, because the two free radicals join together, combine together, resulting into a third alkyl product. But normally it doesn't happen. Some unwanted reaction take place because you are using the atmosphere. So there is a possibility that the alkyl free radicals, instead of reacting with other alkyl group, it start reacting with the oxygen in the atmosphere, resulting into the hydroperoxide, as you can see in this picture. That this is an unwanted reactions. Our intention was to make alkyl group with alkyl, but this couldn't happen, and then some unwanted thing happens, that is the alkyl group, alkyl free radicals start reacting with the atmospheric oxygen, resulting into the hydroperoxide. So such conditions, such situations may come where you have this hydroperoxide product as an unwanted product because of this auto oxidation. This auto oxidation is sometimes can be used at the industrial level for purposely. I mean, this can be used for the production of certain important chemicals. For instance, usually the phenol is produced from the cumene by utilizing this auto oxidation. So sometimes this a reaction can be used for the beneficial or the advantage for beneficial purposes. It could be beneficial. I mean, how it is used, you can see in this picture that the cumene has been allowed to react with the oxygen, resulting into the phenol and the acetone, which are the useful organic. So we can change the benzene ring. We can oxidize the benzene ring to the phenol, and then phenol to the hydroquinone, and then quinone. I think we have already discussed about such reactions, and we have also discussed about the conversion of the cumene into phenol, chlorobenzene into phenol, benzene sulfonic acid to the phenol, and then benzene diazonium salt to the phenol. So these are the very common reactions that we will be again discussing about this, that how these conversions are usually brought about to convert the benzene into the phenol. So how you will do that? The question is that you are required to convert the benzene into the phenol. So what are the available reactions that you can do? So here is the reaction. First of all, you will subject the benzene ring. You will allow the benzene ring to react with the 1-propene in presence of the aluminium chloride as a Lewis acid. It will change this is a simple alkylation reaction where the benzene ring is changing into the cumene. In the next reaction, this is the same reaction that we have discussed just a while ago, that you introduce this oxygen to the hydroperoxidation, where the OOH group is the oxygen is inserting between the carbon and hydrogen, resulting into this hydroperoxide. This hydroperoxide, upon the acid hydrolysis, this is changing into the phenol. This is a simple reaction. Similarly, you can also bring about this reaction, that is to change the benzene ring into the phenol by using the chlorination first in presence of the Lewis acid, and then the chlorobenzene then will be allowed to react with the NaOH and water. So upon the base hydrolysis, this chlorobenzene will be changing. One thing that how to bring about this reaction, changing the chlorobenzene to the phenol using the base and first, and then followed by the acid workup. So what is the mechanism for this reaction? Well, the answer for this reaction is that first of all, in presence of the base, it undergoes the benzene formation. Benzene is an intermediate resulting in this reaction. This benzene is generated by abstraction of the aromatic proton by the base, resulting into this benzene by leaving the chloride group. Once this benzene is produced, this benzene is now attacked by the water, and as a result the phenol is then produced. So here is the mechanism for these conversions also, where the diazonium salt of the benzene, they are changing into the phenol. Same, there is a benzene formation, and then thereafter the acid workup resulting into the phenol. Similarly, the second reaction, you can see that aniline is reacted with HNO2. This HNO2 usually result into the benzene diazonium salt, and then you know that benzene diazonium salt can be leaving as a leaving group by treating it with the base, and then thereafter with the acid hydrolysis it will result into the phenol. Thirdly, you can see that if you are starting with only benzene, then first of all nitration, then reduction of the nitrobenzene into the amine, and then ammonia can be leaved by the benzene formation. So these are all the type of the reactions where you can produce that phenol through. Similarly, what are the reactions where we can make this quinone and hydroquinone? We have already discussed about such reactions, but I will show you again that what are the ways where we can produce this quinone and hydroquinone. As the reaction, you can see that what are the ways where we can use, just using the quinone you can converted into the quinone, and then by the quinone, by using the potassium dichromate, can be changed into the hydroquinone. So in this way you can bring about such kind of the changes